Alright, hello. In this video we're going to look at a different way of finding volumes using a method called cylindrical shells. So, like I say here, we're going to continue looking at this type of problem, but it's a very specific problem. What we have is these solids of revolution still. So before when we talked about finding volumes, it was a little bit more general, and it was that idea of integrating area across a length. Here we're looking at a different method, but for one of the specific cases that we looked at, these solids of revolution. So this is a method to keep in mind, kind of keep in your back pocket with if the disk and washer method doesn't quite work, or maybe doesn't work too easily for us. So the idea is, suppose you have a solid of revolution, and to approximate the volume, you're going to use shells. So what we have in mind here are objects that look kind of like this. So the idea is a cylinder, but with like most of the space in between missing. So I guess a cylinder really would be the shell of the object. So maybe a thick cylinder, if you like, or a filled-in cylinder but hollowed out, or however you want to think about it. But the idea is we've got objects that look like this, so very thin width going around in that cylinder shape. And so the idea then is, if you've got some solid revolution, you're kind of filling it in with shells that are, it's kind of like a, let me say, like a, I'm not going to do a good job here, but kind of a Russian nesting doll type deal, where you've got, it's the worst drawing I've ever made. But you've got these shells kind of building out, filling in the space, sitting one inside the next, inside the next, inside the next. So that's what we're talking about there. If you've got a solid obtained by rotating a region about the y-axis, then the shell at distance x has volume approximately equal to this. And so we want to just make a little bit of sense of where that's coming from. The idea is, if I have, again, this shell, as best I can draw it, and so imagine if I was to take a scissors and cut down that edge there, or down that side. And then if I unroll this, I've got, not worrying about getting dimensions exactly right. This is probably a little bit short, but it's okay for our purposes. So I've got this basically a right rectangular prism now, folded out, and so I can approximate this width, this length, this little width there. So we'll call delta x. This is the third one on my list here. The height is determined by a function value that we'll see in a second. It's the function that defines the region that's rotated about the axis. And then the 2 pi x would be this length here. So the x is really, in the construction of this, our axis of revolution is right here. And so maybe I'll use something instead of red. And so that distance is x if we're rotating about the y-axis. And if we're rotating about something different, then we would adjust accordingly. So if that radius is x, then the circumference, which is really what we're looking at here, is 2 pi x. So here's a sketch of computer-aided sketch of some of the type of thing we'd be looking at. Actually, what this is, and I didn't we actually include the region, but what we've got is y equals this function, negative x squared plus 8x minus 12. So it looks like part of a parabola, something pretty terrible, but something sketched roughly like that. So you might see the region right about in here. So that's the region that's spun around. In this case, the y-axis going right through there. So what we're trying to do with the shells, if you were to do a washer, you can imagine you take this region and spin it around, so it'd be this little bit here, spun around. And you could do that, but it might be really hard to describe. In this case, it would be, because the outside part would be part of the curve, the inside part would be part of the same curve. We'd have to express this as a function of y, which is a little bit tricky. So instead, what we want to do is instead of doing washers, so if I've got, I'm out here, I've got it's hard to see with the graph with the sketching, but hopefully you kind of get the idea. You get this little shell going around that's filling in that just a little bit of space, and then you'd have inside ones, outside ones, these concentric shells, and you'd fill that space perfectly. As you increase the number of those, you're going to fill it in better and better and better if you've got a nice function. And that's going to give us an exact result down the road. Incidentally, this is where we get the delta x part. You get this skinny little part here. And so that height is f of x or f of x asterisk, if you like, for some value. And then your distance was x. We're spinning it around this way. So that's how all those ingredients come together from what we had said before, with the f of x, 2 pi x, delta x, from that shell. So the idea with the computer graphics is it's supposed to make things easier. Maybe it makes it muddier. I don't know, but hopefully you can kind of visualize. You're looking at, again, something kind of like this. You're looking at a bunch of these in here, right? And in the 2D part of it, you're looking at this height spun around for a shell, this height spun around for a shell, this one spun around for a shell, and so on. So formally, here's the description. If S is a solid obtained by rotating about the y-axis, the region bounded by y equals f of x, and y equals 0 from x equals a to b. So it's our kind of standard situation here. I've got some function y equals f of x from a to b. And we're spinning that guy around the y-axis. Then the volume of the resulting solid is going to be definite integral from a to b of 2 pi x times f of x dx. And again, think circumference height and the thickness of the shell, which kind of shrinks to 0 as you increase the number of shells. So adding up all those shell volumes gives us an estimate. That limit gives us the exact value. One last thing, this method is going to apply for objects by rotating about the x-axis if we give suitable changes. So now If we're rotating about the x-axis, for example, rotating this way, then we're going to integrate with respect to y. Our radius is going to be, oops, turned the wrong way. Our radius is going to be a y value, and our height of the shell is going to be this part here because we're going to spin it around this way. So like I said, it works the same way, just make suitable changes, basically swapping x and y as appropriate. All right, so last quick summary. Of course, the more we practice this, the better we'll get. And one of the things you want to just keep in mind when you're setting these up, when you've got these solids of revolution, you can integrate with respect to x or with respect to y. If you're rotating about the x-axis or anything parallel to it, you're going to integrate with respect to x if you're doing discs or washers, and with respect to y for shells. And when you're going about the y-axis, you're going to integrate with respect to y. Oops, trying to match my color code here. For discs and washers, and you're going to go with respect to x for the shells. Again, with practice, this will really be like kind of second nature, but early on, definitely is tricky. So it's really useful to think of these estimating kind of rectangle slices to think about how you're setting the problem up, and getting some sketches of those regions will help as well. But that's the method, and again, something we can use if discs and washers aren't working too well for a solid of revolution, trying to find that volume.